Are we okay to start? Okay. Well, so hello everyone. My name is Francisco Falcón, and this talk is called Exploiting Adobe Flash Player in the Era of Control Flow Guard. So first, the mandatory introduction. My name is Francisco. I am an exploit writer for Core Security. I am from Argentina, and I'm interested in stuff such as vulnerability research, exploitation, reverse engineering, and that kind of stuff. So this is the agenda for this talk. We'll start with a little overview of Control Flow Guard. Then we'll see a quick overview of the CVE 2015-03-11, which was a use after free vulnerability affecting Flash Player, which was the starting point for this research. Then we'll move on to see how to leverage the just-in-time compiler of Flash in order to bypass the CFG mitigation. And also we'll see how Adobe has hardened the just-in-time compiler of Flash. The second part of the talk is about data-only attacks. And we are going to see three data-only attacks against Flash Player. They are how to gain unauthorized access to the camera and the microphone of the user, how to gain unauthorized access to the local file system of the user, and finally, how to execute arbitrary code without using shellcode nor ROP. And we'll have demos, live demos of every of these three data-only attacks. So let's start with a quick overview of Control Flow Guard. Control Flow Guard is one of the latest exploitation mitigations implemented by Microsoft. And this mitigation focuses on making harder to exploit memory corruption vulnerabilities, specifically those cases in which the attacker is able to gain code execution by providing a function pointer that is later called through an indirect call. That is typically the case of memory corruption vulnerabilities, allowing the attacker to overwrite the function pointer, or use after free vulnerabilities in which the attacker can craft a bit table for a freed object, that kind of vulnerabilities. So what does Control Flow Guard do? Well, Control Flow Guard works by checking that the target address of an indirect call is one of the addresses identified as valid at compile time. And this mitigation needs support from both the compiler and the operating system. From the compiler side, it is supported by the latest Visual Studio version, that is Visual Studio 2015. And on the operating system side, it is supported by Windows 8.1 Update 3, which was released 1 year ago in November 2014. And also on Windows 10 since its technical preview. So, one interesting thing about the Flash Player plugin for Internet Explorer is that starting from Windows 8 and including Windows 8.1 and Windows 10, this Flash Player plugin for Internet Explorer is now part of the operating system. It's integrated into Windows, and Microsoft is providing the security patches for it. And this integrated version of Flash is being compiled using the latest Visual Studio compiler, which is CFG aware. And if you really want to know about the internals of this mitigation, I can recommend you these two papers. The first one is called Windows 10 Control Flow Guard Internals by researcher MJ0011, which was presented at the Power of Community conference last year, and also Exploring Control Flow Guard in Windows 10 by Shaq Tang from Trend Micro. So, Control Flow Guard protects indirect calls by putting a call to a validation function before indirect calls. And this is a screen capture from IDA Pro showing that in the Flash Player binary for Windows 8.1, Control Flow Guard is protecting more than 29,000 indirect calls. So let's move on to a little overview of this CVE 2015-03-11 vulnerability, which was a use after free vulnerability affecting Flash Player. And this bug was found exploited in the wild in January this year. And this was the starting point for this research. This vulnerability is a textbook use after free affecting Flash. The vulnerable function is called uncompress via clip variant. This vulnerability happens when decompressing a byte array containing corrupted clip data. This buggy function will free a buffer while it's possible to keep a reference to it in the domain memory global property, which is a property of ActionScript. So the exploitation plan is the regular one for a use after free vulnerability. Once the free has happened, we need to fill that memory hole with some other object. And the typical way in Flash was to allocate a vector object in that memory hole. So the domain memory global property is supposed to point to an array of bytes. But instead, now it's pointing to a vector object that we managed to put in that memory hole. So let's see this in a graphical way. This is the normal state of the domain memory property pointing to a plain array of bytes. But after the free has happened, domain memory can still reference that buffer, and we managed to occupy that memory hole with a vector object. So we are occupying that memory hole with the vector object, which contains the element of the vectors, but also the metadata of the vector, and that contains a pointer to the table and also the length of the vector. And this vector object was really useful for exploitation purposes because we can corrupt this length field, and if we overwrite it with a really high value like FF, we can gain arbitrary read and write memory access to the whole memory process memory. So what was the exploitation approach before the existence of control flow guard, for example, on Windows 7? Well, the first exploitation step was to overwrite the length of the vector in order to gain arbitrary read and write memory access. The second step is to overwrite the bit table of the vector field with the address of our wrap chain. And finally, we need to call a virtual method on that corrupted vector object in order to start our wrap chain. So, what's different when we have control flow guard enabled? For example, on Windows 8.1 Update 3. Well, the difference is in the last step, when calling a virtual method of the corrupted object, for example, the toString method. In that case, control flow guard will detect that we are trying to hijack the normal execution flow when we are trying to call our first wrap gadget, because it is not marked as a valid address, so application will detect this security failure and exit immediately before we can get code execution. At the binary level, this is the part of the code where we can gain code execution in a version of Flash without CFG. It dereferences the bit table of the object, then it grabs the second function pointer from the bit table, and then it calls it at that call edx instruction, which is an indirect call. And there is where we start our wrap chain, for example, on Windows 7. This is the very same part of the code with CFG enabled. Highlighted in yellow, you can see a call to the guard check icall fptr pointer. That is a pointer to the CFG validation function. So as you can see, before doing the indirect call, in this case it is a call ESI instruction, it calls the validation function. That one will detect that we are trying to execute an invalid address, so it will terminate immediately. When control flow guard detects a call to an invalid address, it will execute that interruption 29, which means that the OS has found a security failure, so execution stops immediately. So let's see a few approaches on how we can try to bypass this control flow guard mitigation. Oh, this is just a note for the rest of the talk. I'm probably talking a lot about read and write memory primitives, In this case, I explained before, I gained these primitives by overwriting the length of a vector, but you probably could use any other memory primitives you need as long as you obtain them. So this is a short list of ideas on how to approach ZFG. This is not comprehensive at all because there are a lot more ideas. These are a few things I tried when trying to exploit this. One idea is to overwrite a return address on the stack because return addresses are not protected by ZFG. However, I wasn't able to determine the address of the thread stack from my starting point, so that idea didn't work for me. Another idea is to take advantage of another module loaded in the same process, which may be compiled with no ZFG support. But this is not the case of Internet Explorer because every module is compiled using ZFG. Another approach may be to find indirect calls which for some reason were not protected by control flow guard. Let's focus on this third idea. Ideally, we need an indirect call which is not protected by ZFG that we can call in a straightforward way, and even better, if at the time the indirect call is executed, we have a CPU register pointing to our data, so it's easier for us to pivot the stack and start our rob chain. So, as I said before, when describing control flow guard protects indirect calls that could be identified at compile time. So the question here is, are there any indirect calls in Flash Player which are not generated at runtime, at compile time, And the answer is, yes, there are. So here it comes the just-in-time compiler of Flash to the rescue. The code generated by the just-in-time compiler of Flash does contain indirect calls. And since this code is generated at runtime, it is not protected by control flow guard. So just as a historical note, the just-in-time compiler of Flash has been proved useful for exploitation purposes in the past in order to bypass mitigations. For example, you can take a look at these two papers. The first one is called Pointer Inference and Just-in-Time Spraying by Dion Blasakis, and the second one by Fermin Cernak, which is called Flash Just-in-Time Spraying Infolic Gadgets. So let's see how to leverage the just-in-time compiler of Flash in order to bypass control flow guard. From our action script code, we can create a byte array containing our rob chain. And if we take a look at the internal representation of this byte array object, we can see that at offset 8, we have a pointer to a btable object. And the name of these classes are taken from the ABM Plus source code, which is an open source release of the ActionScript virtual machine. It is available on GitHub, so if you are working on Flash, you might find it useful. So at offset 8 of our byte array, we have a pointer to a btable object. Let's follow it, and here we have the btable object, which contains a lot of pointers to objects of type method emp. And let's focus on the method emp object, whose address is stored at offset 0xd4 of the btable object. Who's calling? So this is the method emp object whose address is stored at offset 0xd4 of the btable. Not again. So the second D word of this method, that's it. Thank you. So the second D word of this method emp object is a function pointer. That is the second one, whose value is 61C0A70. And this function pointer is really interesting because it's called through an unguarded indirect call from code generated by the just-in-time compiler of Flash. Look, this piece of code is code generated at runtime by the just-in-time compiler, so it's located somewhere on the heap. First, we can see here the comments. it grabs the address of the byte array object, then it dereferences the address of the btable object from offset 8, then it grabs the method m object from offset d4 of the btable, and then it grabs the function pointer located at offset 4 of the method m object. And finally, it calls it through that indirect call, which is the call EAX instruction. So it's calling a function pointer with an indirect call, and there's no control flow guard here. And even better, this code can be easily triggered by calling the toString method on our byte array object containing our rob chain. So far, we know how to trigger in a straightforward way an indirect call which is not protected by CFG. What we need to do is to put a pointer to a fake method m object at offset 0xd4 of the btable object. And as an additional benefit, at the time that call EAX instruction is executed, we have the ECX pointer pointing to our data. So pivoting the stack is really easy from there. Let's explain this in a graphical way, which should be easier. There we have our byte array object. This is its internal representation. It contains a pointer to a buffer object, which in turn contains a pointer to the actual data of the array. But we'll focus on the right side of the screen. At offset 8 of the byte array, we can see a pointer to the btable object, and at offset d4, there's a pointer to the method m object right there. And highlighted in red, you can see the function pointer that is called through the unprotected indirect call. So by using our read and write primitives, the idea is to modify that state and overwrite that pointer at offset d4 of the btable, so it looks like this. You can see that now at btable plus oxd4, we have a pointer to our rob chain. So our rob chain will be interpreted as that method m object. So when we call toString on this modified byte array, we'll get an unprotected call to the second D word of our rob chain. So implementing this idea from ActionScript looks like this. First, assuming that we have read and write primitives, first we need to determine the address of the btable object. That is by calculating the address of byte array plus 8. And the target address for the override will be the address of btable plus d4. And then we just need to override that address with the address of our rob chain. Just as an implementation note, you can see that I'm storing the address of the rob chain shifted 3 times to the right, and that is because address of rob chain is a variable of type unsigned int, which internally is represented as shifted 3 times to the left. So this way I'm storing it the way I need it. So finally, we need to call the toString method on the corrupted byte array object. This is as simple as this, and this way we start our rob chain, and we bypass control flow guard. So you may be asking, what's the current status of this technique? Well, Adobe killed it in Flash version 18.0.0.194, which was published in June this year. And as a side note, Google has hardened the vector object in July this year with additional improvements in August this year. So if you're looking to obtain read and write primitives, you may need to find another way because the vector technique will not work anymore probably. So, as I said, Adobe killed this CFG bypass technique. Let's see how they did it. This patch I told you about hardening of Flash, released on June this year, contains 2 main hardening measures for the just-in-time compiler of Flash. The first one is when just-in-time code is the source of an indirect call, and the second one is when just-in-time code is the destination of indirect calls. Our bypass technique is killed the first way, that is when just-in-time code contains an indirect calls. Now, what they are doing is to emit a call to the CFG validation function before indirect calls in the code generated at runtime. In the second case, they are using new memory management flags, which are page targets invalid and page targets no update, and new memory management functions like set process valid call targets, which is a new Windows 10 API. So regarding the first part, that is protecting when the just-in-time code is the source of an indirect call, this is what they are doing. There are no more unguarded indirect calls in just-in-time code. This is what they are doing to kill this technique. As you can see, there's an indirect call there at the call EAX instruction. However, you can note here, highlighted in red, now there's a call to the CFG validation function. So the technique is now dead. So let's see the other part, that is when just-in-time code is the destination of indirect calls. So if you take a look at this article called Memory Protection Constant in MSDN, you can see that when you call virtual alloc in order to allocate a new memory region with execute permissions, all locations within that memory region will be marked as valid call targets for CFG. And in a similar way, if you call virtual protect in order to change the permissions of a memory region to page execute permissions, and that means page execute read, page execute read write, page execute read write copy, I don't remember the exact name, every location within that memory region will be marked as valid call target for CFG. Why is this? Well, this is the pseudocode of just-in-time compilers which are not aware of CFG. First, usually the just-in-time compiler will start by allocating a new memory region with read and write permissions. Then the just-in-time compiler will emit new code and write that code to the new memory region. Then it will give the newly generated code execute and read permissions, so now it's ready to call that newly generated code. But let's see what is Flash Player doing regarding regarding control flow guard in Windows 10, for example, where they have additional protections. Well, Windows 10 introduced two new memory protection constants for virtual alloc and virtual protect. And these constants are page targets invalid and page targets no update. And their value is the same because they do almost the same, right? So page targets invalid is supposed to be used with virtual alloc. It should be combined with execute protections, and using this flag will mark all the locations in the new memory region as invalid targets for CFG. On the other hand, page targets no update should be used with virtual protect, and it should be combined with execute permissions. This flag will indicate that the control flow guarding information should not be changed when assigning the new memory protections. They are also using this new memory management function, which is set process valid call targets. This function is new in Windows 10. And remember that at the first part of the talk, I said that control flow guard protects indirect calls which could be identified at compile time. Well, this new Windows function allows to provide new control flow guard information at runtime. That is, by calling this function, you can provide CFG information with a list of new valid or invalid call targets. So this is like ideal to use with just-in-time compilers, which are generating new code and maybe removing them, so they need to mark them as invalid. So what the just-in-time compiler of Flash is doing now, for example on Windows 10, and taking advantage of these new memory protection constants and memory management function, looks like this. First, the just-in-time compiler starts by allocating a new memory region with read and write permissions. By using read and write permissions, every location in that memory region is an invalid target for CFG. Then the just-in-time compiler will generate new code at runtime and write it to the memory region. And here it comes the difference. The just-in-time compiler will call virtual protect with execute and read permissions, but also using the new flag, that is page targets no update, highlighted in red. This way, they are giving the whole memory region execute and read permissions, but by using this new flag, they are avoiding that every location in that memory region is marked as valid. So instead, they are using the new memory management function, that is set process valid call targets. So they are marking as valid target for CFG just the address of the newly generated function. So that is, they are using a good granularity. So the new code is only marked as valid, not the whole memory region. So that looks really good. So that's how Adobe has managed to kill the technique and also protect against future attacks. That is by leveraging the fact that virtual alloc and virtual protect mark every location as valid when giving it executable permissions. So the second part of the talk is about alternative payloads. So the question here is, what if hijacking the execution flow of a program becomes really, really hard because of mitigations such as control flow guard? Well, we still have data-only attacks. Here, we are ruling out gaining code execution by injecting shellcode or using ROP. Instead, we are focusing on hacking the program by modifying its data, that is, by modifying its internal state. If you are interested in this type of data-only attacks, you can take a look at this related work. All of them are previous presentations from Black Hat, including Easy Local Windows Kernel Exploitation by Cesar Cerrudo, Write Once, Pawn Anywhere, also known as the Vital Point Strike by researcher Tom Keeper, and Data-Only Pawning Windows Kernel 8.1 by Nikita Tarakanov. So, the data-only attacks we are going to discuss in this section are three. First, how to gain unauthorized access to the camera and the microphone of the user. Also, how to escalate the privileges of our flash file, that is, escalating from the restricted remote sandbox to the privileged local trusted sandbox in order to gain unauthorized access to the local file system of the user. And the third attack will be how to execute arbitrary commands without injecting shellcode nor using ROP. So, Flash Player holds an object which I have called the security settings object. I don't know what's the real name. And this object is somewhere on the heap. This object contains some interesting fields. For example, at offset 4, it contains a D word indicating the current sandbox. And at offset 0x49, it contains a single byte indicating if the camera is activated or not. That is, if the user has granted access to the camera or not. This object is somewhere on the heap, but fortunately, we can obtain its address by following a chain of pointers using the address of a shared object, which is an ActionScript object, as the starting point. So let's see how to locate this security settings object in memory. The first step from our ActionScript code is to create a shared object, which is an ActionScript object. And by using our read primitive, let's assume that we have one, we need to leak the address of this shared object. And the second step is using the address of this shared object as the starting point, we need to follow a chain of pointers. That is, the address of shared objects, then with the reference the pointer of offset 18, then 0C, then 9C, and there we have the address of our security settings. But note that if you are trying to port this to maybe a different version of Flash or different operating system, that is Windows 8.1 versus Windows 10, or different architecture, that is 32 bits versus 64 bits, you may need to check that if these offsets remain the same. I'm not sure, maybe they change across different versions of Flash. So you may need to do some reverse engineering. So far we know how to locate these security settings objects in memory. Let's see how we can abuse it in order to gain unauthorized access to the camera and the microphone of the user. So, when a Flash file tries to access your camera or your microphone, Flash will show you this security dialog. Here, Flash is warning you that this site is requesting camera access and that a malicious Flash file could attempt to record you. So it's up to you if you decide to click on allow or deny. But as long as you don't click on the allow button, the camera remains not activated. So our goal here in this data-only attack will be to turn on the camera without user interaction. That is, when the user sees that and doesn't click on any button, the camera will still turn on. So, taking a look at the documentation of the camera class from the ActionScript documentation, we can see that the camera class contains a property called muted. This is a Boolean value indicating whether the user has denied or allowed access to the camera. If we search the Flash binary for the camera.muted string, which is there, there's the camera.muted string, and here we have camera.unmuted string. And before that, there's a call highlighted in yellow, which is a call to a function that I have called isCameraMuted. And this function will just check the value of the byte at offset 0x49 of the security settings object. So, the steps to activate the camera without user authorization are as simple as this. First, we need to find the security settings object in memory. And then we need to set the byte at offset 0x49 of these security settings to 1. And activating the camera will also grant access to the microphone. So, implementing this idea from ActionScript code looks like this. Here, again, we are assuming that we have a read and write primitive. The read primitive should be arbitrary, so we can read from arbitrary addresses, and the write primitive it may be not so powerful. As long as we can change a value from 0 to 1, it should work. First, we need to obtain the address of a shared object. Then we need to follow a chain of pointers, that is, starting from the shared object, we read the pointer at offset 18, then the pointer at offset 0C, then the pointer at offset 9C, and then there we have the shared object, the security settings object. Finally, we just need to set the byte at offset 49 to 1 by using our write primitive. So, once we have done this, we are ready to start capturing frames from the camera, and we may upload it to our server, for example. This is just standard ActionScript code to access the camera. There's nothing special here. It just here takes frames from the camera, and it will use the URL request class in order to upload the captures to a remote server. So, let's go with the first demo. Here we have a Windows 8.1 Update 3 virtual machine with Internet Explorer 11. And this Windows 8 machine is running a vulnerable version of Flash. In fact, it is vulnerable to the CVE 2015-0311 I told you at the beginning of the talk. So, usually when a Flash file tries to access the camera, you'll see something like this. This is just a test Flash application I did to test that there's a camera available. So you usually see this, and as long as you don't click on allow, the Flash file is not able to access the webcam, which I have here, right? So I'll show you a live demonstration of this technique to gain unauthorized access to the camera. This is a showcase of my HTML skills. Pretty nice, right? So I click on this webcam demo link, and it will show the normal screen of the camera. I won't click on the allow button, and anyways, the camera will activate. So I click here. So I'm putting my hands here, as you can see. Nothing is clicking anything. And now, here it is. So now, even the security dialog is there, but the Flash file has access to the camera. So right now, it could be capturing frames and sending them anywhere. So let's move on to the second data-only attack. This is how to escalate our privileges from the remote restricted sandbox to the privileged local trusted sandbox. Flash player loads different Flash files into different sandboxes according to their origin. There are 4 different sandboxes. The less privileged is called the remote sandbox. These and Flash files loaded into a web browser are loaded into this remote sandbox, which is the less privileged one. Then we have 2 intermediate sandboxes, which are called local with network and local with file system. Local with network means that the file is loaded from a local resource and it has access to the network, but it won't have access to the local file system. This is like this because if a malicious Flash file has both access to the network and to the file system, it could try to steal our files and upload them to a remote server. In the same way, there's the local with file system sandbox, in which Flash files have access to the local file system, but they cannot create network connections. And on top of that, we have the local trusted sandbox, which is the more privileged one. Flash files loaded here have access to both the network and the file system. So our goal here is to move from the remote sandbox where our Flash file is loaded all the way up to the local trusted sandbox. So the current sandbox in which our Flash file is loaded can be queried from ActionScript by accessing the sandbox type property of the security class. If we search the Flash binary for the names of these sandboxes, that is local trusted, local with network, etc., we can find that those names are referenced here. I'm not sure if you can see it, but the names are referenced here. It says local trusted, local with network, local with file. And highlighted in yellow, we can see that this code is reading the sandbox type field from the offset 4 of the security settings object. So this field can contain 4 different values, meaning 4 different sandbox types. 0 means remote, 1 is local with file system, 2 is local with network, and 3 is local trusted. So our goal here is to override this D word located at offset 4 of the security settings object with a value number 3, right? So moving from the limited remote sandbox to the privileged local sandbox is as simple as this. First, we need to locate the security settings object in memory. And I explained how to do that by following a chain of pointers using a shared object as the starting point. And then we just need to use a write memory corruption primitive in order to set the D word at offset 4 of the security settings to value 3. So, implementing this idea in order to escalate our privileges from ActionScript goes like this. First, we obtain the address of our shared object by using our read primitive. Then we follow the chain of pointers, that is the pointers at offset 18, then 0C, then 9C. And finally, we use our write primitive in order to overwrite the D word at offset 4 of the security settings object with a 3. This way, we are escalating our privileges to the local trusted sandbox. So, escalating to the local trusted sandbox means that our Flash file now has access to both the local file system and to the network. So, we can steal files and upload them to our server. So, once we have overwritten the sandbox type, that is, at that step, we just can start reading arbitrary files from the local file system of the user. Here, I'm trying to steal a file called secret.docx from the documents folder. And in order to do that, I'm using the file protocol, as you can see at the top, together with the URL loader class. This way, once we get the contents of the file, we are ready to upload them to our server. And this is just standard ActionScript code to send data to a server by using the URL request class. So let's go with the second demo. In this case, I'll try to read the contents of this flag file, which is located on the desktop. It has this text, hello everyone at Black Hat Europe 2015. Let's change it for something else. Say a phrase or a word. Annoying phone. Annoying phone. Right. So, this is the sandbox demo. It will create a specially crafted Flash file which will overwrite the sandbox type of the security settings object in order to escalate privileges to the local trusted sandbox and read the contents of that file in the desktop. So I click on it. So there it is. Annoying phone. So once I have read the contents of the file, I can do whatever I want. For example, upload it to a remote server or whatever in order to exfiltrate arbitrary files. So the third data-only attack is about how to execute arbitrary commands without using shellcode nor ROP. So, as I said at the beginning of the talk, ControlFlowGuard checks that the target of an indirect call is one of the addresses identified as valid. And it is possible to abuse legitimate or safe locations to do something useful from an attacker's perspective. For example, we can abuse it in order to execute commands without resorting to use shellcode or ROP. And let me say that there was an overlapping in the discovery of this technique with researcher Yuki Chen, which presented here yesterday. And he presented this technique first at the SysCon 2015 conference. So kudos to him. So one of those functions identified as valid during compilation time is the winexec function, which belongs to the kernel 32 DLL. Nothing will stop us from replacing the bit-table of an object with a fake bit-table containing a pointer to the winexec function, because this function is totally legitimate for indirect calls. So if we are able to either control or override the first argument that is passed to the virtual method being invoked, we can craft a call to winexec with an arbitrary string as its parameter. So, you should be able to implement this in a lot of ways, but I'll tell you about the particular implementation I did of this technique. I found out that when calling the toString method on a vector object, the second function pointer of its btable is called, and it receives the D word stored at offset 8 of the vector as its first argument. So, by using a write primitive, we could try to overwrite the memory pointed by vector plus 8 with a string of the command we want to execute. For example, calc for demonstration purposes, right? Also, by using a read primitive, we can calculate the address of the winexec function. And we need to store it as the second function pointer of our fake vtable. So, then we need to use again our write primitive in order to replace the vtable pointer of the vector with the address of our fake vtable, which contains the address of winexec as its second function pointer. And finally, we need to invoke the toString method on this corrupted vector object in order to craft a call to winexec receiving the calc string as its argument. And this way, we are executing code without injecting shellcode nor using ROP. So let's explain this exploitation idea in a graphical way. Again, here we have a vector object which contains the elements of the vector at the bottom and also the vector metadata. In the metadata, we can find at offset 8 a pointer pointing somewhere on the heap, and actually I don't know what's there in that memory. I know that it's pointer somewhere on the heap. And I want to overwrite that memory there with the calc string, which is what I want to execute. Also, there's a pointer to a btable, and this is the original btable of the vector, and the second function pointer, highlighted in red, is the one being invoked when we call toString on this vector object. So, the exploitation idea is to create this state. By using our write primitive, we are writing the string we want to execute, that is calc plus the terminating null. And also, we are overwriting the btable pointer, so now it points to our fake btable. And our fake btable at offset 4, that is its second element, contains the address of the winexec function. So, after corrupting the vector object this way, when we call toString on this vector object, that will result in a call to winexec with calc as its argument. So, let's go with the live demonstration of this last attack. So, here we have the last one. Of course, I'll try to execute a calculator. So, I'll click on it, and if everything goes well, we can see a lot of calculators, because one is not enough. Okay, I'll kill all of them because it's going to kill my machine. So, conclusions. Control flow guard is a nice exploitation mitigation which does raise the cost of exploiting memory corruption vulnerabilities. Instead of just starting a ROP chain, now we need to spend time and effort in trying to bypass it. That is, before control flow guard, once we gained code execution, that is, once we can hijack the normal execution flow, we just needed to modify the execution flow in order to start our first ROP gadget. And now it stops us, so we need to spend additional effort and additional time in order to first bypass CFG and then trying to do something. Also, I think that just-in-time compilers are likely to undermine the effectiveness of control flow guard in other software unless people put special effort into hardening them, that is, into protecting the code generated at runtime. Because Visual Studio, that is the compiler, does a great work at identifying valid targets, valid call targets. However, on code generated at runtime, it's a bit different. The developer needs to use the new memory management flags and the new memory management functions. So I think that Adobe with Internet Explorer did it well. That is, they are properly protecting now the just-in-time compiler. But any other software embedding, for example, JavaScript engines which contain just-in-time compilers, or Java, or whatever contains a just-in-time, they may end up undermining the effectiveness of CFG if they are not specially protected. And finally, data-only attacks are really hard to detect or prevent. Here, we are not injecting shellcode, we are not doing drop, we are just modifying maybe single bytes or D words, that is the internal state of the program, in order to obtain some advantage. And I think that we may see an increase in this kind of data-only attacks as modifying the normal execution flow of programs becomes harder and harder due to mitigations like control flow guard, for example. So that's it. Thank you very much for attending this presentation. So do you have any questions? Yes?
So actually, when you use green exit, so you leak the address, you could have also used the function that adds new targets, like the one that the flash chip uses, where the target is just dropped.
First, for the first part of the question, yes. First, I need to some way determine the address of WinExec. For example, as I already had a read primitive, so it was really straightforward. Once I was able to leak a pointer belonging to kernel 32, I was able to calculate its address. And the second part of the question was?
So there is this new function that where you can add
set process valid call targets. I think it should be possible to do it if you are able to prepare the arguments for this new function, which are 5. That is, it's a little bit harder than WinExec, which just takes 1. But I think that it should work. If you are able to craft a call to a valid function, it should work, I think. Yes?
Another question. So, how do other cheats do that? So like the JavaScript cheats, how do you compile it?
Sorry, could you repeat, please?
So you showed that Adobe Flash cheat does it well. Did you look at other cheats, like the JavaScript cheats?
No, I didn't. But I'm pretty sure that unless they are doing something like in a proactive way, maybe they are not properly protecting the code generated at runtime. Also, even this is pretty new. Flash started hardening the just-in-time compiler just in June this year. So I think that other just-in-time compilers may be unprotected, I guess. And there are not just web browsers. For example, I don't know, MongoDB has has a JavaScript engine, so maybe that's not even protected. And I don't know how many applications are using just-in-time compilers. I guess a lot. So, any other questions? Don't be shy. Yes. The vector technique was like the standard way to obtain read and write primitives. So Nowadays, you need to, it's like a challenge, you need to find another way to get your read and write primitives. I don't know what's the current technique to obtain read and write primitives. It probably should be doable, but I don't know how to do it right now. Yes, maybe it's becoming more challenging. At least they are patching the easier ways. That is, overwriting the length of a vector type, so you can index anything in the memory, was like trivial. So I think they are going the right way. That is, at least they are hardening the easier ways. Probably with enough work, you should be able to obtain new memory primitives, but I think they are going the right way. That is, hardening the easiest ones. And as I said before, probably you don't need an arbitrary write primitive. Even having a restricted one, for example, increment by one a memory address may work for you, or something like that. For example, turning a 0 into a 1 may be enough to turn on a Boolean value, so the program behaves different. So I think that you need a powerful read primitive, and the write primitive may be a less bit powerful. Any other question? Yes?
So do you think lots of these attacks could be eliminated by implementing a separated heap that you are only allowed to allocate the same or very similar type of object?
Are you asking if it's possible to protect against this
Isolated heap, yeah. So,
in order to protect against their own attacks?
well, in general, because then you wouldn't necessarily have that same read and write primitive if you had the isolated heap for different type of objects.
Regarding that, I think that protecting data only is, I don't know if it's possible. I don't want to say it's impossible, but it's really hard. There's always something that can be triggered, that can be overwritten, and the behavior of the program will be different. My guess is that using isolated heaps would not change that. But that's what I think. I'm not really sure. There's always something that eventually you can modify in order to modify the behavior of the program. Any other question? Anyone? Well, thank you very much for attending.